Hi, welcome back with another video of Rapid Recovery series. Today we will be discussing about viscosity. So first see what viscosity is and how it works. So first thing is viscosity is all about liquid friction, and that is what it determines the thickness of a liquid. And viscosity is only applicable for laminar flows. Laminar flow is a flow of liquid which flows as layers. So let's consider a laminar flow of velocities of two adjacent layers V1 and V2 and the separation between layers D. So in that case, viscous force is proportional to V1 minus V2 over D, and this is called the gradient of velocity. And as well, viscous force is proportional to A. So by collating these two, Newton came up with the equation of viscosity as F equals eta A V1 minus V2 over D. So this is the general equation of viscosity. This is viscous force, eta is coefficient of viscosity, and A, area perpendicular to gradient of velocity, and this is gradient of velocity. There's a variation for viscosity with temperature. So that goes as this. So which means higher the temperature, viscosity decreases, viscosity of the liquid decreases in a decreasing rate. Viscosity decreases in a decreasing rate. Okay, here, if I collect all three equations we have in viscosity to the single page, first one is Newton's equation as I explained before. Newton's equation is F equals eta A V1 minus V2 over D. So introduction of terms are V is viscous force and eta coefficient of viscosity, A area perpendicular to gradient of velocity, and V1 minus V2 over D is gradient of velocity. And this equation is only valid for liquid layers, for the relative motion between liquid layers. And when it comes to Stokes equation is F equals 6 phi eta AV or F equals 6 phi eta RV. And F is viscous force on a sphere, and eta coefficient of viscosity as usual, R radius of sphere, and V velocity of sphere. And when it comes to conditions of validity of Stokes equation, that is only valid for spheres. And a volume of the sphere should be negligible with respect to the surrounding liquid, and the surrounding liquid should be at rest. And when it comes to Poisson's equation, the last equation of viscosity, Poisson's equation is V over T equals phi delta P A to the power 4 over 8 theta L, where V over T is rate of liquid flow, A radius of tube, and delta P over L is gradient of pressure, and eta is coefficient of viscosity. And when it comes to conditions of validity of this equation, this is only valid for horizontal tubes. Tube should be horizontal, and area of the tube should be uniform throughout the tube. Okay, the next thing is maximum acceleration of a sphere which is moving downwards in a viscous fluid, right? So let's consider a sphere of radius r. Let's consider a sphere of radius r, right? So where if it is moving downwards, viscous force is upwards, opposite to the motion, and upthrust works, mg works. Now if I use F equals ma downwards, mg minus u minus F equals ma, right? Now what happens is, once the object is released from rest, its velocity increases. When velocity increases, viscous force increases. So therefore, this viscous force increases. So left-hand side of the equation decreases. So therefore, from the right-hand side, acceleration decreases. So first idea you have to have is, this object moves downward with a decreasing acceleration, right? With a decreasing acceleration. So therefore, maximum acceleration occurs at the release point. At the release point, V equals 0, right? Maximum acceleration occurs at release point. So make V 0. So mg minus u equals ma. Simplify this. Mg minus v rho g, let's say v dash rho g, equals ma. Since densities are known, we can plug these values as v rho g. So m can be written as v dash rho og. This is v dash rho lg. So this is v dash rho oa. So AMX comes as, simplify this, G times rho O minus rho L over rho O. So this is called the maximum acceleration of an object moving downwards in a viscous fluid. Okay, next idea is about terminal velocity. Now, from the previous step, you know that the object moves with a decreasing acceleration. So therefore, at one point, its acceleration becomes 0 if there is a decreasing trend. So at that point, since it's having a velocity, acceleration becomes 0. There is no external unbalanced force. It starts moving with a uniform velocity. That velocity is called the terminal velocity. So let's see how the terminal velocity is determined. Right. Now my argument is that Since terminal velocity is a uniform velocity, acceleration at that velocity is zero. So make acceleration zero from this equation and simplify. Make acceleration zero. Since A equals zero at terminal velocity, mg minus u minus f equals zero. So which means mg equals u plus f. Simplify these terms. Mg equals u is v dash rho lg plus 6 phi eta rv. And volume of a sphere is 4/3 pi r cube. Love that. 4/3 pi r cube rho og equals this also 4/3 pi r cube rho lg plus 6 pi eta rv. Cancel phi throughout, phi to phi cancels, and 1 r cancels, r squared remains, and this can be cancelled by 2, 2, 2, and 3. Multiply the entire equation by 3. Multiply the entire equation by 3 while taking the terms out. So Vt, terminal velocity, equals 2r squared g rho object minus rho liquid over 9 eta. This equation is called the terminal velocity of a sphere moving downwards in a viscous fluid. These three are the motion graphs of AT, VT, and AT of any object which is reaching a terminal velocity. When an object reaches a terminal velocity, it moves with a decreasing acceleration, and after terminal velocity, acceleration becomes zero. So AT graph is, it is starting from Amax, and acceleration decreases and making zero. And velocity time graph is starting from zero, and at some point, velocity becomes constant, and that particular velocity is called terminal velocity Vt. And you can convert these graphs to AT to VT to ST. If this is converted, this graph will be an increasing displacement with this. So you have to know about these three graphs as well, for the basic variations of AT, VT, and ST of any object which is reaching a terminal velocity. Okay, so I hope you got a good understanding about the most important parts you have to know in viscosity here in A-level physics. Let's meet with another video of Rapid Recall series. Study hard, work hard. Goodbye.